Hello, I welcome you all to your own channel MSK Learnium. This video gives you the information about the dual cycle. Dual cycle is also known as the mixed cycle. Why we call it as a mixed cycle? Why? Because it is a combination of Otto cycle as well as the diesel cycle, or you can say it is the combination of petrol cycle and diesel cycle. So as I said, this is the combination of Otto and diesel. That means the heat will supply at constant volume as well as at constant pressure, but the heat will reject it at constant volume itself. So this dual cycle or mixed cycle is having total 5 processes. As you remember, in Otto cycle and diesel cycle we have only 4 processes. That is, 2 are the adiabatic, compression and expansion, and heat supplied and heat rejection at constant volume and constant pressure respectively for Otto and dual cycle. So in this case we have a total 5 process. So first of all, you have a adiabatic compression. We can say 1 to 2 adiabatic compression. Adiabatic, that is reversible adiabatic compression, right? So it means what? The initially the air will intake into the combustion chamber and it will be compressed reversible adiabatically. Then 2 to 3, you can say the heat supplied at constant pressure volume. 2 to 3, heat supply at constant volume. So 2 times we are supplying the heat, that is by keeping volume constant and by keeping pressure constant, right? Then we have a 3 to 4 further heat supply at constant pressure, right? And finally 4 to 5 adiabatic expansion. Here I am writing reversible adiabatic expansion. Here I forgot, so you have to consider that this is also reversible adiabatic. So it is reversible adiabatic expansion, right? Reversible adiabatic expansion. And next we have a finally 5 to 1, we will reject the heat at constant volume to the initial condition, right? So we can say heat rejection at constant volume, okay. Now, so then these process we will see on the pressure versus volume and temperature versus entropy diagram. So first of all, I'll draw the PV diagram, that is pressure versus volume diagram for the dual cycle, right? So here you can go that for that I'll take the pressure on y-axis and volume on the x-axis, right? So here we have a pressure on y-axis and volume on x-axis. So first of all, adiabatically compression we are doing, right? This is what you have a 1 to 2, means here you take the air, right, and it will be compressed adiabatically up to the 2 point, right? Then after compression we will supply the heat at constant volume from 2 to 3. Again we will supply the heat by keeping pressure constant, which is 3 to 4 process, right? And then we have to expand the gases, that is like this 4 to 5, right? And then 5 to 1 you have a, this is 4 to 5 is expansion and 5 to 1 is the heat rejection. So this is the arrow up, compression, heat supplied at constant pressure, expansion adiabatically, and the heat rejection. So you are supplying the heat 2 times, that is this is as well as this one, and here you are rejecting the heat. So this is your QS, that is heat supplied, and this is also QS. Here you have a pressure is constant and here you have a volume is constant, okay? And here you are rejecting the heat. How? By volume, keeping volume constant. So this is how you have a PV diagram for the dual cycle. Now we will see the TS diagram for the dual cycle or mixed cycle, that is temperature versus entropy diagram. So that's also we'll see. So here you have a temperature versus entropy diagram on your screen, right? So first you will take the temperature on y-axis and the entropy on the x-axis, right? So I am taking temperature on y-axis and the entropy on the x-axis. So first you have a adiabatically compression, right? So let's say this is your adiabatically compression 1 to 2, reversible adiabatic compression you did, and then constant volume, heat supplied at constant volume from 2 to 3, and again constant pressure, heat supplied 3 to 4, and finally adiabatically expansion you did, right? And then you have a heat rejection at constant volume, right? So this is 4 to 5. So arrow is up, 1 to 2 adiabatic compression, 2 to 3 heat supplied at constant volume, and 3 to 4 again you have a heat supplied but at constant pressure. Adiabatic expansion from 4 to 5, and the heat is rejected at constant volume, that is this whole as constant volume. So here you have a heat supplied and this is also heat supplied but heat is rejected. Now we will see the efficiency of a dual cycle or mixed cycle. So efficiency, you know, output by input. So output is what? Net work. That is, net work is nothing but heat supplied minus heat rejection, and heat supplied is what? That is heat supplied at constant volume plus heat supplied at constant pressure. So first of all we can see, and let's say that how much air is intake into the cylinder, that is 1 kilogram of air is entered into the cylinder. So mass we have we will consider that m kilogram, 1 kilogram, right? So you can say the for m is equal to 1 kilogram of air, right? Means air you are intake 1 kilogram, right now. So this is what, that you can say heat supplied, HS is the heat supplied, is equal to what? mCV from constant volume, from where to where? 3 to 4, again and CP at constant pressure 4 to 3. So you can say the total heat supplied is equal to mCV T3 minus T2 plus mCP T4 minus T3, alright. And then you will get the heat rejection. So heat rejection is what? That heat rejection at constant volume itself, that is mCV, from where to where you are rejecting the heat, that is T5 minus T1. Okay, so this is how you get the heat rejection and heat supply. Now next you have to do that, we will see the efficiencies, right? So here you can say the efficiency of mixed cycle or dual cycle. So efficiency of mixed, or you can say dual cycle, right? Mixed or dual cycle. So here you have a efficiency of dual is equal to what? That efficiency of dual is nothing but the output by input, that you can say net work, that is W net by heat supplied, right? And W net is what? Heat supplied minus heat rejection. So you can say W neta dual is equal to heat supplied minus heat rejection by heat supplied. Means 1 will heat supplied get cancelled. So what is that? Dual efficiency, you can say neta dual is equal to 1 minus heat rejection by heat supplied, right? So heat rejection is what? mCV T4 minus T5 minus T5 minus T1, right now? Yes, T5 minus T1. So here directly we'll get the efficiency formula for the dual cycle, that neta dual is equal to, you have a 1 minus 1 by gamma to RC to the power gamma minus 1, right? Under bracket you can write that is RP into rho to the power of gamma minus 1 by Rp minus 1 plus gamma into rho, gamma into Rp, right, gamma into Rp into rho minus 1. So this is the efficiency of dual cycle. That is what? 1 minus 1 by gamma Rc to the power gamma minus 1 Rp into rho to the power gamma minus 1 by Rp minus 1 plus gamma Rp into rho minus 1, where you can say Rc is nothing but the compression ratio, right? Rc is the compression ratio, and Rp is the pressure ratio, right? Rp is the pressure ratio, and rho is the cutoff ratio. That cutoff ratio, you know, when you are supplying the heat at constant pressure, there you will get the cutoff ratio. So this is what you have a efficiency for the dual cycle or mixed cycle. This is the Rp, right? Rp minus 1 plus gamma into Rp into rho minus 1, right? Now we will see the comparison between Otto, diesel and dual cycle. So our comparison on two way, that is at constant at compression ratio and the heat rejection, right? So first comparison we'll see, or you can make a subheading that comparison between Otto cycle, dual cycle and diesel cycle. As you already learned all the three cycles, so that's why we will do. So you have a comparison between Otto, right, diesel and dual cycle, okay, and dual cycles. So first comparison we will see on behalf of, that is first comparison we can say that for same compression and for the same compression ratio and heat rejection, right? For the same compression ratio, right? Compression ratio and heat rejection. Means you have a three cycle, Otto, diesel and dual. All these three cycle is having compression ratio is same and the heat rejection is at the same amount. Then what will happen to the efficiency, right? So in that case, the dual cycle is having Otto is having more efficiency than dual, and then diesel, means diesel will be less efficient, right? So for that condition, that neta Otto is greater than the neta dual, and this is greater than the neta diesel, right? So this is how we can see the efficiency comparison for same compression ratio and heat rejection. Now the one more comparison we can see, which is based on the maximum pressure and temperature, right? We can say next for second comparison you have a for maximum pressure, right? PR is the pressure and temperature, okay, and the heat rejection is same, right? In that case, the diesel will be more efficient than the dual and then Otto, right? So you have a that diesel is greater than the dual cycle, okay, and then it is greater than the Otto cycle, right? So it means that when you have a maximum pressure and maximum temperature is at the same heat rejection, in that case the diesel cycle will be more efficient than your dual cycle, and then you have a Otto cycle, means Otto cycle for this case is less efficient. But when you are taking the same compression ratio and heat rejection, the auto will be more efficient than dual and then diesel. So this is all about the cycles. In next video we will see the problems related to auto, diesel and dual. So please do like, subscribe, comment and share this channel. Thank you.